Okay, if not, we look at the whole idea of phase transition of a fluid from a slightly different viewpoint and derive what are known as the Clausius Clapeyron equation for a phase transition. And so we'll see how to do that. Now take two phases, a two-phase coexistence. So now we have seen that this can now be written as a single equation. A single equation and two variables. So I can express one variable in terms of another, right? Provided certain conditions are satisfied. So this can be my function f of dp, which is actually the difference in the two chemical potentials. Obviously the functions mu1 and mu2 will be different for the two phases, right? So this is what it is. If I want to, for instance, express P as a function of temperature, the sufficient condition clearly is that the derivative, so we are saying if f of xy equal to 0, y needs to be expressed as a function of x, right? Then the condition is that the partial derivative of f with respect to y should not vanish. Right? So this is the reason. Now what is this value? The derivative of mu1 minus mu2 with respect to p. What is that quantity? It's not fugacity. It is what? d by dp of volume. There's a difference in volume, right? So we have seen the basic equation for any homogeneous part is this. Clearly, the derivative of mu with respect to p is the volume. Now I have the derivative of mu1 with respect to p, so that will be p1 and that of p2. That is not equal to 0. Clearly, that is valid for any phase transition. We have seen one of the properties that differs between the two phases is the specific volume. So clearly, that would be satisfied. But we have also seen that the implicit function theorem, the application of the implicit function theorem, also gives an expression for the derivative. Right? So if I have f of xy equal to 0, let's say, there is an implicit relation between x and y. So for y to be expressed as a function of x, right, the condition, sufficient condition is that the partial derivative should not vanish. Of course, at that point, but we can say over a domain, let us say it doesn't vanish, and y can be over the entire domain. We consider the domain where phase transition can take place. And also dy by dx, what is the formula for that? Can you recollect? Minus fy or rather fx by fy. So now, suppose I write dp, this is actually representing the pressure of phase transition. This is actually the slope of the coexistence curve. That's why this is the pressure. The pressure along the 1-2 coexistence curve. That's what you have to keep in mind. So on a plot of the pressure versus temperature, let's say I'm considering liquid vapor coexistence curve. This can be 1 and this can be 2. And this represents the slope of the coexistence curve, pressure versus temperature, between the two phases. Right? That's what this represents. So I am indicating that by marking the fact that it corresponds to 1-2 coexistence curve. Transition between phases 1 and 2 takes place along the curve. Clearly, this derivative represents the slope of the coexistence curve plotted P versus T. That is clearly minus what would now be the substitute for Fx? What would be the corresponding quantity? D by dt. F is here actually the difference between the two functions. So maybe this would be d by dt of this is what is this quantity. This way I already know it's actually b1 minus b minus of what is the numerator? S1. It's actually minus s. So this would be s1 or rather s2 minus s1 divided by b1 minus b2. So I can write this as, it's easier to remember, both are either I can write it as s2 minus s1 by b1, b2 minus b1, or s1 minus s2 by b1 minus b2. So it's the difference in entropies of the two phases, the ratio of that with respect to the difference in specific volume. That is what the slope of the coexistence curve is. This can also be written in a more famous way as h1 minus h2 by d times b1 minus b2. So how is that valid? What is the reason for writing this? Because how is S1 minus S2 equal to H1 minus H2 by 2? How do you get that? Because what is the function that relates H and S? It is G. G equal to H minus Ts. So I can write D1 is equal to H1 minus Ts1. So the temperature is the same for both the phases. So I call it as T. Here we D2. Let us subtract the 2 and recognize that D1 is actually equal to G2. That's what equality of chemical potential means for a pure substance. The equality of the specific Gibbs free energy. From that I can get this. This is what is often called the enthalpy change associated with a phase transition. So it's now the ratio of the enthalpy change to the volume change multiplied by the temperature. Right? So that's what we have. Now let's consider a specific one that we are most familiar with. Liquid and vapor transition. It can be further simplified when you consider a specific transition when we bring in the properties of the liquid and vapor into focus. So let's consider that, and maybe I will just call one as vapor and two as liquid. It doesn't matter what you do. So then dP, now the by our terminology, the pressure versus temperature is the saturation pressure versus temperature. So the dP by dt actually represents the slope of the saturation pressure versus temperature curve, which is a liquid vapor coexistence. So I'm getting now the slope of the coexistence curve can be written as Hp minus HL by E times Vp minus Vl. So we are considering vapor liquids close to the triple point. Consider a small region around the triple point. I can safely write greater than VL. And further, we've always seen that this will correspond to usually fairly low pressures. So the tripping point at the lowest pressure, critical pressure will be usually typically very high compared to. Of course, varies from substance to substance. But if for a substance the pressure is, let's say, the pressure around the triple point is of the order of 1 to 10 bar, which can be considered as sufficiently low pressure, then the vapor phase can actually be assumed to a good approximation to behave like what? At low pressures. Ideal gas. So what can I replace the VB by? So first, I get HP minus HL by TVB, and further, sufficiently low pressure, I can actually replace the VB by actually RT by P. So the P here is P12 because I am all around the saturation pressure curve. So this can be written as HP minus HL times RT square P12. If I take that over there, P sat. I get this famous equation, d 1 over P sat dP sat by dt can be written as P logarithm to P sat by dt. This is probably what is referred to as the Clausius Clapeyron. Can be written as often the Hv minus HL is written as the enthalpy of vaporization. It's often represented by delta H vaporization, right, by RT square. This may be what is called as the Van Hoff relation. You may check the terminology. Right? But this is clear, but there's no going certain approximation. So the Clausius Clapeyron equation is actually here written for the vapor liquid phase, but it's actually valid for, this may be considered as a Clausius Clapeyron equation for any two phases. It's valid for any two phase transition, liquid vapor or vapor solid or liquid solid. However, here I have taken the specific properties, relative properties of the liquid and vapor into account, and at sufficiently low pressure I get the Van Hoff equation. And further, if I consider to a good approximation, that because this is valid only for a small region around the triple point, maybe wider depending on how much, because as we go farther away from the triple point towards the critical point, we said the properties of the vapor and liquid would become closer and closer, right? But actually, I mean, this will not grow up because this is also becoming closer and closer, Hv also. So this approximation will no longer be valid. We should be careful. And also, we're going to higher and higher pressures, no longer can the vapor phase be considered as ideal gas, right? So here, so under all these, so this can be a good approximation to describe. If I know the triple point, then I can trace the liquid vapor coexistence curve around the triple point for a reasonable range of pressure, provided I know the enthalpy of vaporization. Now, the enthalpy of vaporization can be assumed to be approximately constant, because I am anyway restricting myself only to a narrow temperature range, right? So then it leads to this famous relation, the logarithm of P sat, and I can integrate this, because otherwise this is actually a function of temperature also. So I can only integrate it and just leave it as it is. So if I want to now consider it as a constant, then I have only the 1 over RT squared to integrate, which can be very easily integrated, and I get this further famous formula, which can be written as, if I just now integrated 1 over RT squared, the integral would give me a minus 1 over T plus some constant. So this is a famous, this form is probably adopted by typically if you see any standard thermodynamics book, they were actually given a table of saturation pressures versus temperature for many substances. These are usually fitted to a certain form called as the Antoine's equation. It usually looks like this. So the form of the Antoine's equation clearly follows from this. Logarithm of p is inverse of 1 over t, but some additional constants have been added so that the fitting is done efficiently over a temperature range. It doesn't have A, B and C. It's just that they are fitted to the experimental data and it is tabulated. So rather than give the whole table, you just have the constants A, B and C for various substances and you will calculate the saturation pressure. So now this leads to, this is a slightly different approach. This is more fundamental than the Antoine equation, but you can clearly see the form of the Antoine equation is chosen possibly based on the integrated form of the Hoff or the Clausius Clapeyron equation. So I can now write this as, in terms of the value of, this will be minus, so it should be remove the negative sign and write this as, you can see similarly we can also go equilibrium constant, that's in a totally different context. It's also called as a Hoff equation which describes the temperature dependence of the chemical equilibrium constant. It looks very similar to this. This is a totally different saturation pressure, right, relation. So what this means that if I know the, since typically, of course, the Hoff equilibrium coexistence curve ends at the triple point, and triple point for many substances are measured. This helps you to trace a portion of the vapor-liquid coexistence curve with the knowledge of the enthalpy of vaporization at some particular temperature in that range, approximately taken as constant. You have to see the whole cycle of whole thread of approximations, which is the exact and which is the approximating. So clearly, the same approximation will also apply. If you look at the sublimation curve, it will probably come here further down. That's the solid. There, the vapor and solid. This is the liquid solid. We also have a positive slope. So clearly, you can see that the positive slope of the, this is positive, HV is also greater than HL and PV is also greater than PV, so the slope of the curve is positive, and so you can easily see that. And this one, the sublimation curve where directly the solid and vapor can be in equilibrium, sufficiently low pressure below the triple point. Now you can see, if for instance I replace the L by S, obviously this is V remains the same. This will be HV minus HS divided by. Now what about this approximation? Can I assume that it can also be taken? I mean, the vapor volume, it is going to be much greater than the liquid, close to the triple point, probably also going to be much greater than the solid, which is even denser than the liquid. Right? So this would still apply. I can write this as the enthalpy of sublimation times this. And what about this? Could be a valid justification? I mean, valid approximation? Yes or no? Within reason, we are talking about even lower pressures than the triple point. So this we have assumed to be sufficiently low pressure. Certainly, I can make this, and so sublimation, this will not quite work for the liquid solid. Into the density of solid might be much greater than that of the liquid. Certainly we can't model any of the vapor, the solid or liquid cannot be clearly replaced with ideal gas, so we cannot get this kind of a logarithmic relation for the liquid solid transition, but it looks like we can get this for both the liquid vapor and the solid vapor transition. So what this says is that if I know the triple point, then I can trace at least two of the coexistence curves around the triple point with the knowledge of the enthalpy of vaporization and the enthalpy of sublimation. So here, this is something again. I will get. I can do the same thing, because if it is assumed to be sufficiently constant over the temperature range I am considering, then I can trace the curve with the knowledge of this one parameter. So this is somewhat different. If I have an equation of state, of course I can calculate everything as we have seen. Right? But that will be a long-winded calculation. Calculate the saturation pressure and then calculate the enthalpy change and so on. This is somewhat long-winded. This might give an approximate account of the transitions in certain ranges. Right? But the price you have to pay is that you have to know these quantities, because the equation of state will give you everything. Right? But are there any questions on this? Yes? This can be applied. This is still valid. But all these other approximations, this may still be valid. We can take the specific volume of the liquid to be much greater than that of the solid. That might be a good approximation. But we cannot proceed any further. We have to stop here. It doesn't help us in further simplifying. Yes?
So the pressure is high, so there will not be.
Yeah. No, there's no alternative, but this is as a limited validity, that's all. But as we have seen, we have got the equation of the liquid vapor transition can be traced by an equation of state. So we've seen how to calculate saturation pressure and then calculate all the other properties associated with phase transition. Liquid vapor solid equations of state are usually, there may be some special equation of state that can go all the way up to the solid phase as well, but I have not really investigated that. But typically, liquid vapor is when the equation of state is most useful, we have seen. This is another way of looking at the phase transition. With less information, you can get only less information. You need more inputs, and on top of it, it will be valid only for a limited range. It has its own utility, but it is an important part of the literature and you should be aware of it. Now we'll wind up with the point that I made earlier, that even though, for instance, we considered yesterday a general transition between two arbitrary states, which also includes a phase transition. I have all along been saying you have to be very careful about integrating from one state to another, and if there is a phase transition in between, you have to stop and then calculate the change associated with phase transition and then proceed integrating over the next phase. Showed how that is possible. So in that formula, all the formula associated with the in phase, within a phase transition, they are perfectly valid. There is no problem with that. You might need specific heat or you might need an equation of state. You can trace those property changes. However, we said there was a major limitation in the formula that we wrote down for the properties associated with phase transition. Is a fundamental problem in them, because the objection that has been raised is how you can get all the properties associated with phase transition with only the equation of state as the input, when the equation of state is not a fundamental equation, right? And how we can give all the information, including the saturation pressure and the enthalpy, entropy, and various energies of vaporization and so on. And so we take, for instance, the defining equation for the saturation pressure. There is only the equation of state as the input. This at least you can say B is only pressure, volume, and temperature. Saturation pressure, and you can calculate the volume. So we don't need anything else. But other quantities, energy, we saw the formula for Hp minus Hf or Sp minus Sl and so on. They are also dependent without any energy input. We have been able to get all these energy changes also. That has been questioned in the literature, right? And it has been pointed out that this can only be a good approximation far away from near the critical point where the properties of the vapor and liquid do not vary that much, right? So what do we do then to correct this at temperatures closer to the critical point where these relations may not be valid? So for that, the procedure was first suggested by a person named Hoff in 1967, where he showed that now where is the problem? The problem clearly here. For instance, we first load this. So I am considering an arbitrary vapor state. This is only a possible vapor state. This is a liquid state. So to calculate this, I need to only integrate from here to here. We had the formula in terms of integral over volume, but it can also be considered as an integral over pressure. So I integrate up because there is no problem, there is no phase change. The problem comes when you want to calculate mu L. This is where the problem is, because we have always given the caution that you cannot continuously integrate along the equation of state whenever there is a phase transition. That's precisely what I did. I did that because that's what has been followed in most of the books. I knew very well that that was not quite correct. So we are continuing the integration. We are using the fact that there is something here, right, which we are finally going to discard. But I am using that and continuing to integrate along the equation of state to reach the possible liquid state and calculate this. And then I am checking whether they are equal or not. At the phase transition, the both of them will be equal. So this is where the problem is, that what has been pointed out by many people is that we are able to avoid giving any energy input because this integration will induce integration over an unstable part of the isotherm, which doesn't physically exist or doesn't represent anything physically, which cannot be measured at all, right? That is what is the fundamental problem, that we are doing that, and in the process we are violating a fundamental rule. The thermodynamic properties are really not defined over this, but we do get something that we are able to avoid having to give any input in terms of specific keys and so on. So avoid that, what Kahl did was, now how to avoid, so I have calculated this, what I need is a difference between these two states. If I want the difference, the way I do it in the Maxwell rule is continue this integration. Now this is not correct, is what the experts have said, and they have a point. So what is the alternative? So the alternative that Kahl suggested was to calculate the difference between these two without having to traverse this. He said I will directly jump to the critical isotherm. So I have here P, right? And then I jump to the critical isotherm, it is like this, and then I will integrate first. This is because we always want to keep the constant volume, constant temperature part. So I am doing it on the VT plane, right? So we have always found it convenient. I have to reach from here to here. So I will, as usual, as I have done always, I will choose a constant volume path and a series of constant volume and constant temperature paths. So clearly, this is the first segment. I have now started from the vapor Now I hit the critical point and I don't encounter any phase transition in between, because if you plot also the loop, they will be entirely, I don't want to do it because it will further confuse you, but you can easily do it on any standard textbook loop of covering the vapor, and we can just do EV like this. This is the loop of the vapor liquid states, and at the critical point we collapse at one point. That's the point of inflection. So if I am to the left of this loop, safely away from having to encounter any phase transition. So in the process of reaching the corresponding vapor volume at the critical, so this is now what? A constant volume part. Right? So then what I will do is I will remain on the critical temperature, because that doesn't have any liquid vapor transition. This is the idea introduced by Kahl, that he said that I continue to integrate along the critical isotherm. So now that is a constant temperature part. So I reach the critical temperature at the vapor volume, then integrate all along the critical isotherm until I reach the liquid volume, and then I jump to. So this is the path chosen by Kahl. So here I have a constant volume path, but temperature is changing from, let's say this is isotherm corresponding to T1, Tc. Certainly we will get the Cv of the vapor or gas, right? We need, because we have seen that if I want to integrate constant volume but different temperature, I need the Cv input, right? And now this of course is a constant temperature part, so I need the equation of state. Now again I am coming down from Tc to T1 at the liquid volume. That will again involve the Cv of the liquid side of the system, of the substance, right? So we will see now both the specific heats of the liquid as well as the gas will come into the formula. I'll just write down, you don't have to remember this, because this is somewhat outside the scope of this course, but I just want to point out what you will get. So the equation that you will get, and in fact this was not done by Hoff, but it was done by Clapeyron, that he has a very elegant expression for the defining equation. This is now the corrected Maxwell's rule, and this will have the following form. This formula is that it retains the Maxwell's. So this is already there in the Maxwell group, but according to Kahl, and then later on Clapeyron sort of generalized. Kahl derived it only from the Van der Waals equation of state. Clapeyron generalized it to an arbitrary equation. Then many others have done it in different form. But the interesting point here is now this integral over T1 to Tc that we are doing. There are two parts, T1 to Tc here on the gas side and T1 to Tc again on the liquid side, right? So both of those have to be combined. So this part remains as it is, and the quantity within bracket is CBL. Now an integral over temperature from T1 to Tc, and you can see why that is coming. So you have two parts, one at constant volume of the vapor from T1 to Tc, another from Tc to T1, the constant volume of the liquid, right? That's a constant volume, two constant volume parts, and they are now combined. Plus you also get an additional term which is plus T1 d square t by dt square, which is now because it's an integral over t, so it has temperature here also. The T1 is coming here, the actual temperature at which I want the saturation pressure. This is now an integral over T, 1 minus T1 by T dt. So I don't want you to worry about the dt formula or the derivation. But clearly, what you can see is this group that multiplies 1 minus T1 by T. I want you to focus on that, right? This term. Suppose that term is identically zero. That's now a function of temperature, right? Because this is P1 L to V1T. That's now an integral over volume that is coming within the integral over temperature. Right? So now, if this curve is zero, that is CPL, suppose this is zero, then you can clearly see that the generalized Maxwell's rule will reduce to the Maxwell's rule, but not otherwise. Now, if you look at this carefully, you will also recover the criterion that Kahl obtained for the van der Waals equation of state. That is interesting to see. The van der Waals equation of state is this. Now, what is d squared t by dt squared for van der Waals equation of state? Zero. Right? dp by dt is r over v minus p. This has constant. This doesn't have any temperature dependence. dp by dt is r over v minus p. d squared p by dt is identically zero at all states. Right? So for the van der Waals equation of state, this integrand itself vanishes. So again, for the van der Waals equation of state, the condition is effectively CBL is equal to CBG. That's what I get. What this says is that this gives you an insight as to when the Maxwell's rule may be valid. Now you know by simply looking at the table, if you take the specific heat of liquids, right, water let's say, and look at a specific heat of vapor, right, what do you normally find at a given temperature? Which one would be larger? Specific heat of liquid versus specific heat of vapor. Any substance you can take. Vapor will be larger or liquid will be larger? Vapor will be larger. That's not true. If you go and check the table, specific heat of liquid is much larger. You can easily explain physically why that would be the case. You will find that typically it is quite at a given temperature, it will be quite different, right? But however, we have seen that closer to the triple point, the properties of the liquid and vapor will become. So this condition, which is the condition for van der Waals equation, because here the d squared p by dt squared is there within the integral, it's difficult to see its implications for a general equation of state. For a van der Waals equation of state, equations of state like the van der Waals equation of state where d squared p by dt squared is identically zero, you can see the condition you get for the Maxwell's rule to be valid is that the specific heat of the liquid must be equal to the specific heat of the vapor. Now, whether you are confused about which one is greater or not, certainly you don't consider them to be equal by any stretch of imagination. They will be quite different. Just as the vapor volume and liquid volume are different, the specific heats also will be quite different. The liquid is a completely different phase compared to the vapor. You can see how wrong one could be, right, if you are using Maxwell's rule, unless you are close to the triple point where this condition may actually be satisfied, because the temperature is an important parameter. It will not be satisfied at all temperature, but closer to the critical point where the properties of the liquid and vapor become closer and closer and sort of collapse at the critical point, you expect this condition to be satisfied. So this now gives the reason behind why it would be advisable, it would be in fact convenient to use the Maxwell rule closer to the critical point, because we don't need the specific heat data then. I can directly use just this portion of the equation. But clearly, without proper investigation, I cannot neglect this term completely. Because CBL minus C, of course I have to calculate the whole integral and see how the integrand actually, the difference contributes to the, we have to see the relation of this with respect to these two terms. So it needs a bit of analysis. Maybe you cannot assume it to be negligible, closer to the triple point. Now this gives a practical, because here I explained there is a problem with integration along the unstable and so on. It's a very theoretical criterion or argument, right? But this is a more concrete argument. You can focus just on van der Waals type equilibrium state and say the condition for Maxwell's rule to be valid is for the specific heat of the liquid and vapor to be the same. You know from pure physical considerations that cannot always be valid. Right? So this gives a more practical and easily recognizable condition as to why the Maxwell's rule is actually flawed. Right? So we have to use the more general equation, but the price you have to pay is we have to know all this data of the specific heats. That is why books tend to gloss over this, and this is much easier to use. But fundamentally, this now makes sense that you have now got the specific heats as inputs required, which is what is required even to calculate the saturation pressure, because after all the saturation pressure is calculated from an equality of the Gibbs free energy, which is also an energetic quantity, and you can now see that to calculate that difference, we now need the specific heat data also as part of the input, and this is perfectly consistent with what we expect in a phase transition. So that problem with the Maxwell's rule is overcome by choosing. This is also important because we also see the role of the critical point even practically. Right? And practically, if you want to reach from one state to another, let's say I have state 1 and state 2, liquid to vapor, right, without having to deal with the phase transition. Because practically when you have to deal with two phases processing and all that will be more difficult. Handle two phases. So one thing you can do is to go around and reach the vapor phase by going around the critical point. It also has a practical implication. So by going around the lead to the processing in the supercritical region and so on, above the critical temperature. Is a very important practical region. So the critical point offers you the fact that the two-phase transition stops at the critical point, gives you an opportunity to reach a vapor state from a liquid state or a liquid state from a vapor state without having to deal with the two phases. You can go around the critical point and reach the other phase. You can create a new phase without having to encounter a phase transition directly. Right? Something like that is adopted here for a theoretical reason, because we don't want to integrate along this. So we completely avoid this, because this is the area, the region over which the two phase coexistence exists, and you get all these loops. Right? Outside that, we can safely integrate without worrying about phase transition or having to integrate along the unstable part. That was the idea used by Kahl, and it was later on generalized by Serrin to derive this new corrected equation. Are there any questions? But this we not directly deal with in the code, as long as you are comfortable with using the Maxwell's rule and the associated. So similarly, all the other quantities, Hp minus HL, will also have these as the inputs. You cannot just get it from just the equation of state alone. So your formula will also be much more complicated. Right? So it is definitely a more complicated formula, but requiring more inputs that may not be readily available. Right? But yet, if you want to correct values corresponding to an equation of state, that's the price you have to pay. You have to recognize that the Maxwell's rule cannot be expected to be valid far away from the critical point. Any questions?
At critical point, almost like volume of at critical point, the volume of liquid is almost equal to the volume of gas, no, sir.
At the critical point.
What does it mean for physically? What does it mean,
So
sir?
physically it means that as you go towards the critical temperature, the two phases, that is what it means in terms of the phase diagram. You don't have any transition beyond that. So the properties of the two as the temperature, as a property exhibited by a substance. I can't give an example. It's a description. Why that happens, you have to go to the molecular level and see. But phenomenon that you observe and that you should remember, as you reach the critical point, from the critical point, all along you will have two phase coexistence. The properties of the liquid and vapor are moving closer and closer to each other. And at the critical point, they will become identical and you can't have two phases beyond that.
It means only one gas phase, sir.
Gas, you can call it, yeah, we have probably gas certain unique properties. Around the critical point is a major point of interest for physicists because some fundamental discontinuities and all that are there. They call it second order phase transition and so on. But around the critical point, you have very high compressibility, for instance, in the supercritical state. Right? So it is more like a gas. You can regard it like that, but it is only one phase. But it has also certain properties which are closer to the liquid as compared to the gas. For instance, diffusivity of the supercritical phase would be much higher than compared to the liquid. So that is why it combines in some sense the good properties of the vapor that you want in terms of processing and the gas and the good properties of the liquid also. Right? It in some sense combines the two. Right? I don't know if they say high computer, I'll check that, but there are certain advantages. It seemed to be a good compromise for both the liquid and vapor, and that's very useful in processing. I'll clarify that what exactly it is, or those properties, right? But it gives, that's why you go to specifically do the processing in the supercritical state, and that's particularly true for carbon dioxide, whose critical temperatures and pressures are very low relatively. So you don't need to exert too much, spend energy to bring it to the supercritical phase. We'll clarify that in the next class.